Hi, welcome back to my channel. And in this video, we will be having the continuation of the basic set theory for kids part 2. So as continuation of what is being discussed on the part 1, so we will consider again the concept of subset. So as defined, given two sets A and B, we say A is a subset of B and denoted by the symbol if all elements in A, or let's say we just say this way, if for all x in A, x is also in B. So let us say, for example, you have set A here, another set, we have set B here. So if you will find an element here, 1, 2, 3, you should find 1, 2, 3 to make sure that A is a subset of B. So regardless, you will find elements here 4 and 5, and A does not have 4 and 5. It does not matter because the point here is that A is a subset of B. Now in this case, since A is a subset of B, we write this in the symbol, or shall we say we write this. We can say that A is a superset. I'm sorry, B is a superset of A. That's it. So that is now the definition of a subset. Now, from that subset, what do we mean by a power set? Okay. A power set of a set A denoted by this symbol is the collection of all, so meaning there's all subsets of A. So say for example, your A here is the set containing 1, 2, and 3. So the power set of A is the set containing 1, the set containing 2, the set containing 3, the set containing 1, 2, the set containing 2, 3, the set containing 1, 3, the set containing A, of course, because A is a subset of itself. And of course, let's not forget that the set containing empty. So meaning to say that another fact here, empty is always a subset of any set. Okay, so if you might notice, this is actually 1, 2, 3, 4, 5, 6, 7, 8. So meaning to say that the cardinality of the power set of A is 8. Actually, there is a formula for that on what is the cardinality of a power set of a given set. So the cardinality of a power set of a given set. Say A is given by this 2. That means you take the cardinality of A, and that cardinality will be the exponent of 2, and that is the cardinality of the given power set of that set. So if you notice earlier that A is 1, 2, 3, implying that the cardinality of A is 3. Now earlier, the cardinality of A, of the power set of A, is 8. So this is actually 2 to the 3. So that is the cardinality of A. That's it. So if you have any questions or clarification, you will comment down there on the video, and I will be more than glad to answer all your questions. So let us continue. For that, since we have introduced the concept of a subset, let us introduce the concept of a universal set. So when we say the universal set, it's actually the superset of all the given sets. So meaning to say that you have set A here. Let's say this is set A. This is another set B. Your universal set is actually the superset of all the sets available. That's why it's called universal. Okay, because we have introduced the concept of universal set, we will introduce the concept of the operations of sets. So let me introduce here. So it's actually called a binary operation, but I don't use the word binary because we can just generalize the operations to a more complicated operation. But anyway, let's introduce the concept of the basic notion. So let's start with the union of sets. So to define on that, we say X is an element of the union of sets A and B, denoted by this symbol, if X is an element of A or X is an element of B. Now, before I'm going to explain this concept of operation here, let me introduce the other operation so that we can have comparison of two operations available. So let's introduce the intersection of sets. Intersections of sets says that we say X is an element of the intersection of A and B. And we denote the symbol if X is an element of A or X is an, I'm sorry, element of B. Now, you would say the difference here. Now, if you notice, they look exactly the same definition, but there is a difference. Of course, first is the symbol for the union is this one. The symbol for the intersection is this one. Another thing you have to consider is for the union, there is a presence of or. That means here, this is a logical operator, and this is for the intersection, that means it's and. So back on the basic logic, when we say or, if you have two premises, so either of the two is true, the result will always be true. Now, when we say and, both of the premises should be true to get the result of true. Example, if we say Diane is a girl or a boy. So of course, when we say it's a girl, this is true, this is false. But the entire statement is actually true because you're using the word or. So as long as there's a presence of the truth statement, the entire statement is true, something like that. Although it does not make sense when we use this example, but for the purpose of the illustration of this definition, I'm going to use this. And when I say instead of using or, I use and, so there's a presence of truth and false statement. So the answer is false because the yan cannot be both girl and boy at the same time. Okay, so that is the concept of the true, the or in ands in the statement. Now let's go back to the definition for the union and intersection. So when we say the union, so that means as long as ax is present in a, or it's present in b, or it's present in both, then that's present to the union of the two sets. But if we say that X is a presence of A but not a presence of B, then that is not a presence of the intersection. It should be present to both. So meaning to say, the word that you have to remember synonymous to this is combination. So you have to combine. This is you have to get what is common. Okay. So let us consider, for example, you have set A 1, 2, 3. Your set B is 3, 4, and 5. So if you take the union of A and B, you'll have to combine everything because we say that 1 is an element of A and the union of A and B denoted by one element of A union B. If 1 is an element of A or 1 is an element of B. Although 1 is not an element of B, but this is or, so it's entirely present in the union. So you write 1, 2, 3. There's 3, 4, 5. That's it. Now, on the previous video, we defined that a set is a collection of a well-defined object. So this is uniquely well-defined object. So since 3 is the same as 3 here, so I don't have to write this twice, but just to write these 3. So the union of A and B is 1, 2, 3, 4, and 5. Now for the intersection, so the word that we have to consider is what is common. So what is common to the 2? That's 3. That's it. Now to picture these things out, we will show the Venn diagram for this. So let's say you have a universal set, because again, universal set is the supersets, the superset of given sets. So our given sets here are A and B. So suppose this is our A, this is our B. So when we say the union, let me create another one first. This is your A, this is your B. So when we say the union, so everything in A will be covered, everything in B will be covered. So that is our Venn diagram. Now, when we say intersection, so what is really the common here is only the intersection. So this is just covered. That's it. So these are two of the basic operations of sets. So the union and the intersection. Now let's go to the next definition of the operation of sets. So let me introduce to you the difference of two sets. So we say X is an element of the difference of A and B. Denoted by X element of A and B. So this is just read as A minus B. So that you may not be confused, some books would actually use A minus B. But for the purpose that we can distinguish between the sets and a normal number or a normal element, so I use this notation instead. If X is an element of A, but X is not an element of P. So you can only say that a certain element is the element of the difference of the given sets if that element is an element of the first set but not on the second set. So meaning to say, if we have a Venn diagram here, let's say this is our universal set, you have our A here, you have our B here, you only have to take those elements that are in A but B does not have it. So let us say, for example, our A here is 1, 2, 3. Our B here is 3, 4, 5. Then A minus B is those elements that B does not have, like 1 and 2. 3, on the other hand, is in B, so we cannot write 3 here. That's it. So this is just this different when we say B minus A, because we have to enumerate all elements in B that A does not have. Like 3 is in A, so we only write 4 and 5. That's it. Now let me introduce to you another definition here. The concept of the complement of sets. So we say X is an element of the complement of A denoted by if X is not an element of A, but X is an element of the universal set. So what is that? What does that mean? It only means one thing. You are actually getting all the elements that A does not have to get the complement of it. So let us say, for example, by the way, this is a symbol for the complement of A. So it looks like there's a small c on top of it, or some books would actually use this symbol instead of A complement. But it's like a prime. It's like taking the derivative, but it's not. The Venn diagram for that is here. This is your universal set. This is your A here. So taking the complement of A, you're actually taking what is not in A. So you're actually taking outside A, but inside universal set, of course. So say, for example, your universal set contains 1, 2, 3, 4, and 5. Your A contains 1, 2, 3. So A complement is 4 and 5 only. And by this definition, we would have a remark saying that A union the A complement is the universal set, and A intersection A complement is empty because there's no common to these two. Therefore, the result is empty set. And lastly, we would introduce the definition for the Cartesian product of set. This Cartesian product of set would actually give the rise of the definition of relation and would eventually turn into function. But we would not go by that far. We're only considering the definition of the operations of sets. So the Cartesian product, okay, how do we define that? We say the ordered pair XY is, okay, let me just replace this the notation instead. We say that the ordered pair AB is an element of a Cartesian product with B. Product B. And we denote this symbol. I'm sorry. So this is the Cartesian product. If the first pair of the ordered pair is an element of the first set, and P is an element of P. So something like the first entry here in the ordered pair is an element of the first set. The second entry is an element of the second set. So given example, we have, I'll just make it a smaller set here. You can make it big if you want to. Let's say I just use 1, 2. I have here 1 and 3. So A cross B is the ordered pair. So I'll take one element from A, so that's 1, and I'll pair it with an element in B, so that's 1. Another is another 1, and that's 3. And you have 2, 1, and you have 2, 3. That's all. Okay, so we have now studied about the 5 basic operations of sets. So there are a lot of operations, but actually they're a result of some manipulations and extensions due to researches of many mathematicians. So this is just basic operations of sets that I will lay that will actually give you the foundation on analyzing higher math problems. So this is good for kids. So if you have problems, questions, clarification, you can comment down there on this video in the comment section. You can also request if you'd like to. And that's all. So I'll be more than glad to answer all of your queries. So if you have questions, again, don't forget to comment down there. So that's all for now. And thank you so much for watching this video, and have a great day.